Um, so they call them special purpose outlet, electrical heating and air conditioning. I call them dedicated circuits. If you have electrical heat and or air conditioning, you are talking about dedicated individual circuit for each one of these loads. Can I have thumbs up, Chad? We know that. So that's dedicated individual circuits that are going to be feeding for these equipments. So let's see what we can focus on these guys. A few things. Um, a few things I would like to highlight as we go through resistive heat. We'll talk about resistive heating cables. I don't know how many of you guys have installed resistive heating cables embedded in the walls or the floors. We talk about electric furnace, not gas furnace. The electric furnace, how to size it, and the electric baseboard heater. So basically, and also they have a heating pump, which is reverse function of the air conditioning. I call it reverse function. The air conditioning becomes a heat pump. These are our three parts that you can heat. 1, 2, 3, and 4. 4 ways that you can heat a house. 4 ways you can heat a house electrically. Electrically. Obviously, non-electrically, what do we use? Natural gas or some type of. So these are electrical ways of heating a house. Anybody can think of other ways? There's probably a combination of also resistive electrical heat tape in the floors or the cables. Or you can put a baseboard heaters. The baseboard heaters, guys, in the apartment, we put them in where? In the common stairways, we put a baseboard heater. Or electric furnace. These are not gas furnace. These are electric burning furnace. They burn electricity and they're controlled and powered by electricity. You guys know the difference between electric furnace? All furnaces are powered. The fan is electric, but electric furnace is burning electricity as well as powered and controlled by electricity. Can I have a thumbs up? We know that, Chad? And so an electric bus and a heat pump, again, it's a reverse function of air conditioning. Instead of cooling, it brings it heats the building. So that's what we're going to be talking about. Variation of voltages. This, you're going to hear this one all the time, guys. Every time you have a resistive load, Jeff, they will tell you variation of voltage in a resistive load. Because if the voltage goes up and down, the resistive load substantially goes up and down. So that's, and we talked about, I don't know if you guys remember, plus or minus 10%. That's what typically NEMA standard for the equipment. So they allow you to go higher 10%, lower 10% of the nominal voltage, and the equipment will continue to work kind of within expectation. You go further than this window, then equipment start malfunctioning. Okay, so that's basically a few topics that we'll talk about. Then we're going to move into heating, ventilation, and air conditioning equipment. That's your AC units. I promise you guys, next quarter we're going to be talking about chillers. Now we're going to move. In dwelling, typically we use a split unit packaged air conditioning unit where we have part of it outside, part of it inside. That's typically what we use in residential. We go to commercial, we start talking about cooling towers, and we start talking about chillers and air handling units. And that will come when we go to the commercial. So this is not what we, so we'll talk about this one and the AC requirement for it in a few seconds. We talk about if you have an HVAC equipment, you guys remember that you have to have a receptacle. Anybody remember how far the receptacle have to be from the AC equipment for maintenance? Anybody remember? 25 feet. If you have an HVAC equipment, heating, ventilation, or air conditioning equipment, you have to have a receptacle within 25 feet of that equipment for what? Maintenance. And then there's a couple of SEERs. If you guys remember the SEERs, SEER 13 and all these are terminology that our friends, the mechanical contractors use when they assign a label, an efficiency label for the equipment. So that's basically what this chapter is talking about. This one is just, anybody has an electric furnace? Electric powered burning electricity furnace? No? Okay. So some people, guys, use, typically, I believe in rural areas, sometimes they use it as a supplement to the heating element that they have, or the power element, or the energy element that they have. This is just a few things about the electric advantages of electric heat. As you might know, quiet, clean, safe. So you can read through this one. No fuels, electrical fuels. No fuel tank, especially if you live in a rural area, you don't have to have fuel tank for it. So these are advantages. No chimney is not cool. Does not remove oxygen for the most part from the air because you're not burning natural gas. So these are advantages. Why electric heat? What's the disadvantage in our area here? It's more expensive. More expensive to heat homes with electricity, at least in our area here, than to heat it with natural gas. My understanding is that's why most of us use natural gas as furnaces, right? Powered furnaces. So these are a few things, just FYI. This is for an electric furnace, not for an electric powered furnace, burning electricity. This is how we size that boy, and I can't emphasize how important this one is. It's electric furnaces, guys, are electric heat. They are electric heaters. And when we size them, the NEC code book talks about an article 424 central electric heating equipment. Individual branch circuits, you have to bring in an individual branch circuit for them. Okay, dedicated circuit, individual. And the way they size them, very simple. Very, very simple. Two things. Number one, you take the full load current of that equipment, multiply it by 1.25, and from here you're going to size conductors, and also from here you're going to size overcurrent protection device. Done. Is that how easy that would be? Continuous load. Why 1.25? Because continuous load. So you take the kW of your furnace, right? Divided by the voltage, that will get you the amp, right? You get the amp, you take the kW of the furnace divided by the 240 voltage, that will get you the full load current. Multiply it by 1.25, size the conductor, multiply it by 1.25, size the overcurrent protection device, done deal. Cool? You still need a disconnect. The same thing, the disconnect, you need the disconnect here. Either the circuit breaker will act as your disconnect, otherwise if you have a fuse like this, you still have to have a disconnect within inside of that piece of equipment. Typically the circuit breaker or the fuse disconnect will get you there. Must disconnect the equipment from all ungrounded, shall have a disconnect. So these are basically, this is it, really. This is, in a nutshell, this is how an electric furnace is. Any comments, any question? Dedicated branch circuit, 125 multiplied by the full load current to size overcurrent protection device, as well as the conductors. I want to bring to your attention, guys, there's also a control circuit here that goes to a thermostat. The control circuit is called class number 2 circuit. Class 2 circuits are control circuits. They are wired with 16 and 18 and typically 16 and 18 wire gauge, thermostat wire they call it, thermostat wire. And a couple of things about this particular circuit, that's your control circuit to the thermostat. A couple of things that you have to understand. You can't put the thermostat circuit, class 2 circuit, in the same conduit, the housing, the power. There's some exceptions for that, but class 2 circuits have to be separate from the conduit. They can't enter the same conduit, the same box, the same enclosure with power circuits. So I have two circuits here. I have my power to power the equipment, and I have my control to control the equipment. Typically the control circuit, guys, will be 18.2 or 18.4 wire, 18.2, 18.4 thermostat wire going to a thermostat to turn that heater on and off as needed. Can I have thumbs up, Chad? We understand fully what this is. If this was had this been a gas furnace, you know what the difference is? Everything stays the same. The only difference, instead of having, look at the size here, is 100 amp. I have almost that's a problem with electric heat. 100 amp, 240 system, 240 volt, 100 is 190. I think it's can't read it from here. I thought it was 100 amp. The size for this particular one, 98. So it'll go to 100. The standard, next standard is 100. So I have 100 amp branch circuit, 240, 100 amp branch circuit, 240 going to power and burn electricity to start this furnace. That's if it's electric furnace. Had this been a gas furnace, that 100 amp branch circuit turned into a tiny little one of 15 amp, 120, just to power the blower and to power the control system inside the furnace. Can I have thumbs up, Chad? We got that one? So everybody knows what the difference between an electric powered furnace and a gas powered furnace, or a gas burning furnace and electricity burning furnace. Look at the, can you guys see the size from 100 amp to 15 amp? Why? Because we're burning natural gas. We're not using electricity to burn and get the heat. We're using electricity just to blow the air through the blower and energize the control circuits inside the furnace. Any question, guys? Any question about that? So if it's gas furnace, 15 amp, the same control circuit, by the way, class 2 circuit will go both of them. Class 2 circuit. This is gas furnace. This is electrical. Any comments, any questions? Now we know how to size the gas, dedicated 15 amp circuit, 120. We know how to size the electric. The electric, typically, this is how we size it. Typically, you're looking at probably at least 60 amp service, 60 amp 240 or higher. That's kind of the range that you get them in, 60 amp 240 all the way to 100 amp 240, typically. So they're a big chunk of your load. Any comments, any questions? Can I have thumbs up, Chad? We understand that one? Kerry, my friend, does it make sense? No, yes? Okay, so that's basically it. Again, this is how they do the calculation. Like we said, I can't emphasize the 1.25. This one is a full load current, and you get 98. Then they're assuming, guys, the logs are rated for 75. If it's 100 or less, you're going to go to 60, right? Jeff, like Chad said, or not Chad, the rule in the code says. But this, they're telling you, we know the logs on both sides are rated for 75. So it's size based on 75. Based on 75, you end up with this size conductor, and you end up with this size fuse, and you end up with this size disconnect switch. All these sizes came, look at that. This came from here, and this came from here, and also these came from here. Very easy. One calculation. Done deal. If you have a circuit breaker, you're done. You don't need a disconnect. Your circuit breaker will act as your disconnect. Can I use a snap switch with an electric furnace as a disconnect? Snap switch with an electric burning furnace. No, because you don't make a snap switch for 100 amp 2-pole. So he has to have a disconnect like these one on the wall. Can I have thumbs up, Chad? We understand that fully in electric furnace, because that's kind of a new concept. Okay, the second one is cable. Heating cables, guys. Heating cables, these are cables, they put them in the walls or the ceilings, and they plug them in. They're self-regulated. They plug them in with a 20 amp circuit, and it heats that area. Self-regulated. Typically, they're in the walls, as we said, above the ceiling. Keep the wiring. You have to keep all the wiring away within. When you use this in the cable in the ceiling, embedded in the ceiling. Here's what you need to do. If your equipment are surface mounted, you have to maintain a clearance of 8 inches from where the cables are. If your equipment are recessed, you have to maintain a clearances from the cable of 2 inches. These are all, guys, from the article 424, tells you how to install them and keep all these electrical equipment 2 inches away for if it's recessed, 8 inches if it's surface mounted. So you have to separate these cables as you put them. You have to separate them from the electrical equipment. So that's what we need to worry at least about this one. Electric furnace, we saw the source of the heat for an electric furnace is always the resistance. So they have multiple resistance. They burn them and they get you the electrical heat. Okay, listed. We talked about voltage variation. For all these guys, they give you a voltage variation of 98% plus or minus from the full voltage. Not biggie. There's a factor that they use for the voltage variation. I have a feeling that. Okay, so cable, heating cable, as I said, you guys embed that specially designed cable, embedded in walls or ceilings, wired with a dedicated 20 amp circuits, typically self-regulated, done. So you just bring a circuit, you feed that cable, but there's a couple of rules about installing the cable. Obviously, you have to keep them, as I said, 2 inches away from recessed electrical components like fixtures and fans, and 8 inches if they're surface mounted fixtures on the wall, on the ceiling. They come in different colors, guys. The heating cable in page, I don't have it here, page 488. They go, if your system is 120, they use the color yellow. If your system is 208, blue, 240 red, and 277 brown, and 480 orange. These are, Jeff, that was on German exam at one time. Now these are color-coded heating cables, not power, not electrical wiring cables. They're just heating cables, specially designed cables that have impedance. You put do you know what the cables are, guys? They just put the circuit through them and their impedance, resistive load, and it keeps heating and self-regulated. It self-regulates itself. So anyway, so that's basically what you need to know about that one. In terms of okay, this is really interesting factor, guys. So correcting factor. So voltage. So if you take this, they call it CF equal V for the voltage. Square this, divide it by, this is V voltage, applied voltage. This is voltage, rated voltage. V R rated square V for A. Okay, so here's what happened. To summarize, every time you double your voltage, your power go 4 times. Every time you double your voltage, double the voltage, your power will increase 4 folds. Every time you cut your voltage by half, your power will be reduced by 1/4. Where am I getting this? So okay, suppose that I increase, if you guys look at, if I double my voltage, so this one basically, this will become the voltage applied over the voltage, it becomes 2, right? And square the 2, it becomes what? 4. So my power are increased by 4. If I cut the voltage by half, this becomes here 1/2 to the power squared, and this will be 1/4. If you take this factor and multiply it by the rated power, your power will be cut by 1/4. It might not mean a whole lot to you guys. It means a lot to the electrical utilities that we do all these transmission lines. Take this. You have a 4160 distribution line coming to your neighborhood. Your neighborhood grew and they're sucking more power. You have 2 options. Now either you can go change the conductors into bigger, fatter conductors at 4160, right? Or you can increase the voltage that these conductors are carrying. Granted, you have to increase the insulation too. Okay? So suppose that we are in the city of Bloomington and I have a transmission line 4160 coming to my house, and the utility look how cool that is. You're going to enjoy that one. So I have a transmission line 4160 coming to my neighborhood in Bloomington. We run out of juice from the same conductor. Say 1/0 conductor going, right? We run out of juice from it. 2 options. Increase the conductor, bigger, thicker, more wind is going to tip it, right? You don't want bigger conductors. Or increase the voltage level. So have a different transformer and up the voltage into another 13, they call it 13,800 volt. Okay? So just change the installations, same conductors for the most part, and have another transformer that up the voltage into 13.8. Look what happened though. Look what happened. If apply the same rules, so the voltage used to be what? This used to be V, the VR here. This is now V applied, VA. So if you apply this rule, guys, take the 13, I need somebody to do the math for me. 13.8 divided by 4,160. This is your CF factor. Can anybody tell me what the multiplier is? How much? 3.2. Okay. I will have, out of the same conductor, the same structure, 3.2 more power than what I used to have. Does that make sense? Does that make sense what increasing the voltage does to the power? Oh, I'm sorry, I have to actually square it yet. Oops, I have to square it. So I have to square this, and because this is also squared. Can you square the 3? That would be 9, 10? 10.24. Okay, here you go. So when you square it, it becomes 10.24. 10.24. Now I have 10 times little bit more than 10 times more power from the same transmission line. Does that make sense, guys? See what the difference when they go to a higher voltage? Now, obviously, going all the way back from a transmission line all the way where we are, if your voltage, if your heater is rated for 240, and you accidentally, like Chad did, if your heater is rated for 240, and you accidentally power it with 120, okay? You're going to square this, you're going to get 1/4. Anybody have done that? 1/4 the power. I did a motel one time. Did I tell you this story, guys? We powered baseboard heaters in the motel. They're all 240, all of them 240. There was, I can't remember, 10, 15 of them. Everything is cool. When I'm done, the owner a week after, he calls and he said, Chad, all of them are working perfect except that one guy in a hallway. It looks like it's working, but it's not working right because it's not giving me the heat that others are giving me. He's comparing them together. So what would you do if you're an electrician? Well, your friend Chad, for one of them, I powered that particular one after, working a lot of hours and confused or whatever. I powered that particular one with 120. So this is where I was. And instead of giving me this amount of power, it gave me 1/4 of amount of power because it's rated for 240 and I gave it 120. This only works for heaters. If you did this one in a motor, you will know immediately about this because the smoke starts coming out. Does that make sense? CMF. Yep. So you will hear immediately from it. So this is a big concept, guys. A big concept, bigger than that class. Baseboard heaters. Here's how we size baseboard heaters. Anybody can tell me the magic multiplier that we use? Jeff, what's the magic multiplier for all heaters? Continuous load. 1.25. That's it. 125%. That's the same thing. Baseboard heaters, we size them 125%. We size the conductors and overcome protection device. There are two types of thermostat that they use to control these babies. There is what they call it line voltage thermostat and low voltage thermostat. We'll look at them to control these. So amp rated if they're line voltage. So that's basically it. Here's what we're looking at. Here's your baseboard heater that you guys designed for Chad in your building, right? Here's my baseboard heater. I need 20 amp. We give them dedicated 20 amp circuits each for the most part, guys. Though we can put them in a different circuit, in one circuit. We can. Based on the load, I have 242 poles, say 20 amp circuit. I brought this one into, this is called low voltage thermostat, into double pole single throw. They call it double pole single throw. All this is relay. It has a disconnect here, so that would act as my disconnect too. And I have my thermostat as a low voltage 24 volt thermostat. So when the thermostat kicks in, what happened? You energize this coil with 24 volt. And what happened when you energize this coil with 24 volt? Bam, bam, closes. My heater is coming aboard and up it goes. When the thermostat calls for the heat, you don't need it to heat anymore. It goes down, it heats up, and it turns you want to turn it off. This will open, de-energize the 24 relay. You guys did relays, right, with us? You de-energize the 24 relays, it pushes these, it releases them, and it opens the thermostat. That's called low voltage thermostat. The project that you did, Andrew, my friend, for our project, we assumed this box was part of the thermostat, part of the baseboard heater. So we didn't worry about it. We just provided a feeder for it. Can you have thumbs up, Chad? We understand that fully? So that's your baseboard heater wiring. I want to bring to your attention, guys, the code allow you to re-identify the white conductor as black to be used for baseboard heaters. Article 424 allow you to do that. Article 424 allow you to do that. Can I have a thumbs up, Chad, that we know that? Now, you can only do it if you're wiring with what? With cables. Can I re-identify if I'm wiring with conduits? No, because you can pull any color you want in a conduit. In cables, we're limited. Like in this case, this cable will be 12-2. 12-2, guys, is black-white, right? So how are you going to, but both of them are hot, so you can re-identify the white as a black, allowed by the code. Any question, guys, about this? Any question? All these loads, that's 240, you can wire them in a cable by re-identifying the white. Okay. Permanently re-identified. Again, here's where it tells you re-identification of the conductors with a tape, typically a tape that you put around it to re-identify it. Okay, so we have, this is called low voltage thermostat. Anybody knows why low voltage? Because this thermostat is 24 volt. Everybody can see that this thermostat works at 24 volt because of the transformer here. Now take this. If you go back to this, where's the transformer here? Nothing. This is called line voltage thermostat. So line voltage thermostat, I've done a few of these, line voltage thermostat. So you buy them, put them in a wall, bring the circuit in, circuit out, and the thermostat is built into this 2-pole thermostat, and it turns it on and off part of that whole module or device that you buy. Same thing, re-identification, 12-2, and your 20 amp circuit here. Any question, guys? Any comments about this? Everybody knows that we can re-identify the white as a black to use it as a hot. And number 2, we need to have a disconnect here. Here's what acts like a controller disconnect. It has an off position where you can act as a disconnect. And granted that there is a main disconnect here in the building as my circuit breaker. Everybody knows the line and the low voltage, the difference between the line and low voltage. Why this is called line? Because this is rated for 240. Anybody disagree with that? The voltage that's coming to is 240. The one that we were just looking at, the thermostat, there was a transformer that dropped it down to 24. Any comments, any questions? Aaron, my friend, does it make sense? When the voltage here is 240 here, there's no transformer, then this has to be 240. If there is a transformer, then drops it down to whatever the transformer is dropping it down, typically 24 in this case. Okay, since we're dealing with heat, and if you guys remember, your friend Chad talks about enemy number 1 of electricity is what? Heat. Heat. You can make number 14 carry 40 amps if you don't care about the insulation melting and smelling, right? If you don't care about that one, no problem. Keep powering that boy. That's why the utilities love putting their conductors overhead, guys. See where all the transmission line coming all nationwide. Where do you see them? Overhead. Why do you think they don't go underground and they get mad for underground? They can't go underground. Well, number 1, it's expensive. Why it's expensive? Because for that conductor that you put overhead, you need that conductor that you put underground. Anybody knows why that conductor underground versus that conductor overhead? This one is on the pole on the air, naturally cooled, right way up another 60 feet above ground, sitting like this. Look at the air that's flowing around it and cooling it at all times. Whenever you heat it, it's natural cooling, conduction. You bury that boy underground, you need it to be thicker with the same amount of amps. And of course, when you put it underground, there's also the water and the insulation, deterioration, and a bunch of other things. Okay, because of heat, they require you guys to have the conductors that you tie to them, they have to be rated for 90 degrees. This is where NMB comes big deal. NMB is rated for 90 degrees, no problem with that. Some of these baseboard heaters, guys, they have receptacle outlet built into them because when you put them on a wall, now you screw up the 6/12 rule for residential. So where you have, well, I put it right here. Now I can't put a receptacle because I bought a 6-foot baseboard heater. So the smarter than Chad, the manufacturer, say, we'll solve this problem for you. We will have a built-in receptacle inside the baseboard heater. But do me a favor, though. Power it separately. So you have a circuit that power the heater, circuit 1. Circuit 2 will power the receptacle with the other receptacles in the area. They do it commonly. You look at a couple of, because of baseboard heaters, a lot of things, guys, they don't want you to put the receptacle above the baseboard heater. Anybody knows why? Like baseboard heaters right here, and put my receptacle right here, so my cable is dangling right at the top of the of the heater. You're going to burn your extension cords. So that's a couple of, here's what they're talking about, guys. This is, everybody knows why this is a violation, right? You have to put it to the side, and this is what some manufacturers, a lot of manufacturers can get you. If you have a baseboard heater, they can get you a built-in location where you can put the receptacle. So in a case like this, for this baseboard heater, I will bring a 20 amp circuit to feed this baseboard heater, and I will bring another 20, let's just say 15 amp circuit here to feed this receptacle among other receptacles in the area. Any questions, any comments? Any questions, any comments about these baseboard heaters? Sometimes they have a wall-mounted heaters, guys. They use them a lot in the bathrooms. So same thing, if it's a heater and a fan, when you deal with it, you take a 1.25 times the full load current of the equipment, size the circuit for it. Should be located, okay, available without built-in thermostat. The last thing, guys, we're going to talk about is the heat pump. Heat pump looks like an air conditioning, and except it takes the air, instead of cooling the building, you can use it at certain time to take the heat from the outside and bring it to the building. From the outside or from the underground system, pipe system, you take the heat, you circulate this hot water into your building. So it acts like a reverse function air conditioning. How do we size that boy? We size exactly the heat pump exactly like an air conditioning. We're going to see in a second here. All these equipment must be grounded. Did I get you guys to understand? If you later on when you start sizing things for me and I want to ask you where's your equipment grounding conductor, it goes with everything. You have to have an equipment grounding conductor. There is a circuit called shall not be used, which is a grounded conductor, cannot be used as an equipment grounded conductor. Everybody knows that? There, like I said, for electricity to work, you need only a hot. For it to work efficiently, you need a neutral. For it to work safe, you need what? Equipment grounding conductor. These are three separate things, shall not be interchanged, right? You can't use a grounded conductor as a grounding conductor, or vice versa, and you can't use an ungrounded conductor as a grounded conductor too. So these are every circuit that you guys have, minimum, every circuit, single phase, you need to have a hot, you need to have a neutral, and you need to have a ground. If you graduate from Dunwoody without knowing this, that a minimum of any circuit, you need a hot, a neutral, and a ground, single phase. You go to three-phase circuit, it becomes a hot, and another hot, and a neutral, and a ground. And sometimes you don't pull the neutral. It depends upon the load. Sometimes we go two hots, but the ground, look at the ground, is always where? There. The ground is always there. Your ground airing can be a separate conductor or can be the shell of that conduit right there at the top. That acts as an equipment grounding conductor too. Can I have thumbs up, Chad? We understand that one? With equipment grounding conductor? Perfect. If you have a room air conditioning, guys, the units that we do, typically these are dedicated individual circuits, a 20 amp that you can put it either as 120 or 240. So if you have a window air conditioning typically, and your window air conditioning as a 240, this is a window, so you're going to have a 20 amp circuit typical with these are what, number 12 conductors. And if you have a single phase, typically, here's my neutral, the same thing, 20 amp circuit, and these will be my number 12. This is typically how we use with window air conditioning, dedicated 20 amp circuit, Any comments, any questions? Okay, leakage detection, we don't want to do that. 240, 120, these are receptacles that you can get. Here's the receptacle that you can get 240 only, and this is the 120, 240. If you can look at the top is 120, 240, and the bottom is 120. Okay, moving on into, guys, they use central air heating and air conditioning. That's where you have the furnace and the inside unit of the air conditioning and the outside unit of the air conditioning, of course, out. So that's your split unit system. Um, so a couple of things, guys, about the heating and cooling systems. As you can see, we will talk more about this in the commercial too. It's heating, ventilation, and air conditioning. We have a whole dedicated article for this business, a whole dedicated article. The only thing I want to summarize for you right now is three things. When you have a unit like this, you have to have an overcome protection device, and you have to have a disconnect, and you have to have the equipment. So the way they size the overcome protection device, guys, based on this article, you go 1.75 times full load current. And the way you size the conductor is 1.25 times full load current. We will do a lot of calculation about the air conditioning, guys. Can you guys remember the 1.75 that's coming? We will do a lot of calculation about this. 1.75. That's really when it's an air conditioning unit. What makes the air conditioning different than any other motor they're in? Very simple thing. They have hermetic refrigerant motors compressor. So this is the term that they use to distinguish between an air conditioning and non-air conditioning, because otherwise it's a motor, right? So if you have a refrigerant with a compressor and a motor, of course, to drive that compressor in one package, that will move it from Article 430 to Article 440, and it becomes a special type of motors, and the code treat it completely different, and they assign a 440 article for it. The reason for this, guys, if you have a refrigerant, then your motor compressor combo can be abused more because you're cooling. There's a lot of cooling business going on, so you can push that motor harder to make it work harder than if this motor was driving a fan. Does that make sense? So the smarter than Chad years ago decided, well, since it's a motor and can be pushed hard because there's a refrigerant that's coming out of the whole compressor and cycle of refrigerant cycle, we're going to make a standalone system and we throw it in a different article. How do we size? What do we care? When we size look at this, guys, when we size the conductors, 1.75 instead of 2.5. Remember 2.5? And for the conductors, 1.25. For the disconnect, we still use 1.15 times full load current for the disconnect, when we size the disconnect. We will do a lot of calculation on that one. How about the controller? Almost always the controller for the air conditioning is split. Part of it will be inside the outside unit of the air conditioning, and the other part, of course, will be inside the inside unit of the air conditioning, which is the furnace combo. Why do they split them? Because of that called unique characteristics, the way they work. Any comments, guys, about the HVAC equipment? So if you are airing as we start sizing and say, Chad, which article am I going to go to? Article 440 or Article 430? If you hear the word hermetic refrigerant or compressor, you know that will shift you to one article. I want you guys to wake up for these terminologies that you use with them, which is very, very important terminologies. They use a few terminologies with them that's called rated load amps. Okay, if I can get you guys to understand that if you have an HVAC equipment like air conditioning, you're going to have these terminology, and please understand them now because it will make your life much easier as we move forward. The first one is, guys, rated load amp. The first term that they use is RLC. These are right on the nameplate. You find RLC. This is equivalent to the full load current of a motor. Full load current of a motor. Equivalent to a full load current of a motor, and you size it exactly like full load current, basically like full load current of a motor. Okay, the way they define this one, it's really interesting. I don't think it's at least equal to 6% of the hermetic refrigerant motor. So it has to be this usually as more or equal to 60, and I'm talking 64.1% of multiplied by MCC. Maximum continuous current. The second term that they use, guys, is maximum continuous current. Maximum continuous current is the largest amount of current that this air conditioning can handle before the smoke starts blowing inside it. The largest amount of current that this air conditioning by manufacturer they can handle before smoke starts coming out of it. And they define the maximum continuous current as must operate for current in, okay, this value is 156% of the marked RLC. So this is this value is 156% times RLC. So they define, this is, I will get rid of this one because it's really confusing in this case. So here's the full load amp. This is your full load amp for the machine. This is 156% of this value is how the air conditioning can handle before it starts smoke coming out of it. FYI only, we don't use it a whole lot. The third one is called branch circuit selection current. Branch circuit selection current, because the air conditioning has compressor, fans, control, they have two values for it, full load amp. They have full load amp based on rated load current for the equipment and branch circuit selection current. In the nameplate, you're going to find one or the other. And you're going to use this one as your full load current, basically. Minimum circuit ampacity, number 4. That's your conductor size. Conductor size. Maximum overcurrent protection device, number 5. Maximum overcurrent protection device, that's a fuse or circuit breaker. And locked rotor current, number 6. This is the largest amount of current that the motor can handle when it's locked. When you go grab that lock to lock that motor and not allowing it to move, that's the highest amount of current that this motor is going to encounter if it's stalled. Okay, any comments, guys? Any questions before I highlight the very important, the 3 very important values that you have to understand before you move forward? The most important values that you have to understand, guys, is this value, must understand, and this value, must understand, and this value, must understand. 1, 2, 3. Done. On a nameplate of every air conditioning or a chiller, and nameplate of every air conditioning or a chiller, you're going to find these values, these 3 values.
It's RLC, not FLC.
Rated load current, yes. That's how they call them, rated load current instead of full load amp. So you're going to find minimum circuit ampacity. That if you say 50 amp minimum circuit ampacity, that's how the conductor size, you're going to size for 50. If you find maximum overcurrent protection device that says 50 amp, you're going to stick a 50 amp fuse if they say fuse, and a circuit breaker if they say circuit breaker. Done. And this rated load current is if you don't have these two, then this is how you multiply, this is how you get this. You get this one, guys, by multiplying 1.25, multiplying this number by 1.25. That's how they get this, MCC, if it's not there. How do they get this one? You get this one if you multiply 1.75 multiplied by RLC. So take RLC, multiply by 1.75 will get you MOP. Take the RLC, multiply by 1.25 will get you the MCC. Can I get you guys to give me a thumbs up if you understand at least these 3 ones? Because these are the most important ones, the 3. The rest of them, good to understand, but really has no value in the design. Yes, sir.
The MOP in here, it says you multiply that RLC by 2.25.
Well, it goes from, it's actually a range. It goes from 1.75 all the way to absolutely 2.25. If it doesn't start, we'll get into that one. You start with 1.75. That's your minimum. If it doesn't start, that's what the code say. Then you go as high as 2.25. You're absolutely right. It's a range. Okay. Any question, guys, about these? So, Aaron, when you go to air conditioning and it says minimum circuit ambiguity of 50, you're going to say, oops, now I'm going to go to 310.15b16 and find a conductor that can carry 50. When it says maximum overcome protection device of 60 fuse, you're going to say, I'm going to have a disconnect like this right next to it, and I'm going to stick a fuse, not a circuit breaker, a fuse. Why? Because the manufacturer say the fuse, you stick with the fuse. If they say circuit breaker or fuse, then you have the option. Any comments, any questions about the air conditioning, guys? We will do calculation as we move into the air conditioning. These guys are energy rating. So when you buy, we don't buy we don't buy the equipment for the most part. These are mechanical contractors when we buy the equipment. But you're going to hear about SEER 13, I think. What is this? I don't know what 14. SEER 13 and 14. The higher the SEER, and you know what a SEER is, seasonal energy efficiency rating, how efficient the equipment is. The higher the SEER, Aaron, the more efficient the equipment is. That's as far as we're concerned. We don't specify these equipment for commercial industrial building. Our friends, the mechanical contractor, do. But when they do it, they have a lot of acronyms that they use, guys. Efficiency, energy efficiency, here's an EER. And then here's this value, and these three things that they use, especially the SEER I'm familiar with, they use to get you efficient equipment. Okay? Again, I don't spend too much time on it. You guys can read them for one simple reason. Because nobody's going to hire us for the most part to size the air handling unit or the chiller. We power them. We send conduits to power them and disconnect them, but typically that's under the jurisdiction of our friends, the mechanical contractor. Be aware, but these are because we're environmentally friendly nation, right? And these are the terms that they use to make the equipment, size the equipment to be energy efficient. There's a term, non-coincidental load, guys. Please highlight this. 220.60 tells you the non-coincidental load. If you have a chiller and an electrical boiler, do you think when I size the feeder, do I need to size the chiller? So here's a service here, and I have a boiler, and I have a chiller. Do you think that your boiler is going to be running with your chiller is running? Are you going to be heating and cooling the building at the same time? Typically, no. You might have to bring a little bit of heat and cool in the heat in the winter, in the summer, and cool in the winter, but we're talking about fully heating and fully cooling. No, these are called non-coincidental loads. So, just simple thing. If the size of this boy was 50 kW, and the size of this boy, just for the sake of it, was 60 kVA. When I size the feeder, when I size the feeder, do I need to add them up, or I only take the largest? Can I have thumbs up for the largest? The largest. Anybody knows why? Because it's highly unlikely that they will be running fully at the same time. They call them non-coincidental loads. You're going to hear Chad talking about these when we size the service. Our service, guys, non-coincidental loads. So in a case like this, you drop this and you size this feeder only based on what? 60 kVA. Make sense? Because they're not going to be running at the same time. They're not, that's called non-coincidental loads. Okay, the NEC guys require a receptacle. Please highlight this article too. 120 single phase 15 or 20 amp receptacle must be in an accessible location within 25 feet of the AC equipment and cannot be connected to the load side of a disconnect. Side of the equipment connecting means does not connect receptacle to the load side of the equipment disconnect means. Load side of the equipment disconnect means. Okay? Everybody knows we have to have a receptacle. Take this. I have a AC and I have a disconnect here. Here's my disconnect. My overcome protection device here. Can I do this? Can I come from here and put a receptacle? Can I put this? Can I come from here and put a receptacle? No, because this one called the load side of the disconnect. Why? Because if you disconnect the equipment to work on it, what's going to happen to the receptacle? Dead. Can I do this? Look at this. Can I come from here, from this side, and put a receptacle here? Yes, the line side. This is called line side load side. Line side load side. In a commercial building, guys, they do them a lot where they have a disconnect, have a receptacle, right? Part of the disconnect is a receptacle, but fed from the line side with fused and fed from the line side. So it will save you pulling a 20 amp circuit all the way up to the rooftop unit. We'll talk about this as we reach it. This is just about moving the gas meter clearance of 3 feet away from the electrical meter because of arcing between the equipment. And I think let me see what we have here before okay, we got any source of ignition, any arcing or sparking equipment, a switch. A meter could be a disconnect, it could be source of ignition, right? Because any source of ignition is every time you interrupt the load, you get a little arc. So every time a magnetic starter, a relay, all these are source of ignition. Okay, we talked about these guys, the furnaces and all this. Talk about this, talked about these. Oh, here's another one. Can I put, oops, not here. Can I put 2 heaters on 120 amp circuit? No problem. What's the rule? The rule, these are continuous load. So take this. If that was, let's just say that was 5 amp, and that was 5 amp. So here's how you calculate it. You take 5 plus 5 equal 10, right? 10 amps. The whole circuit, right? Cool. And then you take 10 amps, multiply it by 1.25, and what would that give you? 12.5 amps. 12.5 amps. Suppose the 5.5, right? 12.5. Cool. Everybody's okay with that one? So what's the next standard overcapacity protection device? 15 amp. What's the conductor that goes with 15? Number 14. Done. Can I group them and put them from the same thermostat? Yes, it depends upon the size, their size. So whatever size, you're going to go by the size. And I have done a few of these guys where the size small, you can group 1 or 2 or 3 of them, put them in the same branch circuit, no problem. It depends upon the size. Now here's a situation where suppose this was 10 amps and this was 10 amps, okay? Now you take 10 plus 10 equal 20. Now 1.25 times 20 is what? Anybody can give me? 25, right? It's 25. 25 amp. Now here's a moment of truth. Now you can do this 2 ways. You can either go put a 25 amp circuit breaker and you have to pull number what? Number 10, and feed each one of them with number 10. The problem is your lugs might not be rated for number 10. Most likely they will be. So you feed them with number 10. That's one option. Or you say the heck with it. I'm going to feed each one of them from a 20 amp circuit. So this is when you separate them. Make sense? So my rule is, if I can feed them with a 20 amp circuit, 1, 2, or 3 of them, I put them with 20 amp circuit. If I can't feed them from a 20 amp circuit, guys, it will be too much to put that many eggs in one basket, and it's a good idea to separate them. Make sense on that one? Okay, so that's my heaters. Is the heaters. A couple of locations, you guys look at this. For the heaters, I can put the circuit breaker above the blank part of it here, so it's not dangling over the heater itself. There's a few applications where you can use that. Baseboard heaters. A couple of things, guys. This is the split. This is a split unit. Let me see if I can do what my friend told me to do here. There you go. This is a split unit. The only thing I want to emphasize about the split unit, guys, you bring a feeder for this equipment. Can you guys see? This is outside, and you bring also another 15 amp circuit here. This is my 15 amp gas furnace, right? Typically, what we brought is a 2-pole here and this is 30 amp typically, right? Here's a 30 amp feed to the outside unit. Here's a 15 amp feed to the inside unit, to the furnace. Everybody's cool? And then I will bring to your attention, guys, there's also this is control circuit that goes between the two equipments, as well as between the equipment and the furnace. And these are called class 2 circuits. Class 2 circuits. That's our involvement. Our involvement, actually they're here. That's as far as our involvement, this is coming from the panel right here. This is the feed here, and that will be the 30 amp. And this is coming from the panel here. That will be the 15 amp. And that's basically our involvement in this system, right? So we brought power. These are power. And this is control. Right? That's it. The rest, there's the refrigerant. We'll go through, guys, the refrigerant line and how it works and all the stuff. But for the time being, our electrical involvement in this system is we provide a circuit, a disconnect, and an overcome protection device here, typically 30 amps, and an overcome protection device here, typically 15 amps. This is 2-pole, this is single pole, and this is 240 system, this is 120 system. Make sense, right? That's it. That's how you wire a split unit air conditioning or heat pump. The same thing for the heat pump. Same application. Can I have thumbs up, Chad, that we know how to do that? Cool. Okay, so that's basically our involvement in this system. We talked about the furnace, guys. The furnace is connected. We sized that one. Furnace split. Okay, the last thing I want to talk about here, guys, is there's a couple of requirements for disconnects. Look at this requirement. Air conditioning nameplate. Look at the nameplate. It says fuse 40 amps. Fuse 40 amps, and I put a circuit breaker 40 amps here, and a disconnect with a 40 amp fuse. Have I met the code? Can you guys look at this? The nameplate says they need a fuse of 40 amps, and I put a fuse of 40 amps here and a circuit breaker here. Am I cool? Good? Mm-hmm. Yeah. Why? Because they ask for a fuse, you give them a fuse. If you can't put the fuse here, you have to put the fuse outside. Cool? Can I have thumbs up? If they ask for a fuse, you give a fuse. You got a circuit breaker, give circuit breaker. Okay, so that's scenario one. So look at this scenario now. Look at this scenario. Now, here's what they did. Here they asked for a 40 amp fuse maximum. Chad went and put a 40 amp circuit breaker. And is there any fuse here? And non-fuse disconnect. Just no fuse, just a disconnect. Can I do that? No. Why? Because they're asking for a fuse. Either I have to put the fuse in here or I have to put it outside here, somewhere. Not a circuit breaker. Can I guys get you to understand if they ask the nameplate, ask for a fuse, you put a fuse. And you can put a fuse two ways. Either you put the fuse right in the panel. Most of the time in residential, guys, we don't have a fuse panels anymore. We have circuit breaker panels. So you can't put a fuse in a circuit breaker panel for the most part. You have to put it where? Outside. Most of them, guys, most of the nameplate will say fuse or a hacker circuit breaker. So either a circuit breaker or a fuse. Look at this. Now I have a nameplate, all by the nameplate. It says a fuse or a hacker heating and air conditioning rated circuit breaker. They have a circuit breaker. A lot of circuit breakers are, guys, rated for inductive heat and heating and air conditioning, rated for this type of, for the characteristics of the air conditioning. They call them hackers. So this says a fuse or circuit breaker 40. Okay, so I put no fuse here and I put a circuit breaker here. Did I meet the code? It says either put a fuse or a circuit breaker. I only put a circuit breaker here with 40/40. Am I good? Mm-hmm. Yeah, because it says circuit breaker or fuse. All right, so can I get you guys to understand that the rules is, these are the rules. If it says fuse, you put a fuse either in the panel or outside by the disconnect. You still need a disconnect. Here's your different type of disconnects. Lock rotor amps. Okay, so that's basically all what I have for you. Any comments, guys? Any questions about this? I promise you we will do a lot of actual calculation for these because that's what they hire us to do, sizing for air conditioning. So what we're going to do next week, most likely, all the stuff that I told you, we'll take a heater and we do size everything for the heater. We'll take an AC unit and we'll size everything for an AC unit. So that's it. And a furnace, everything for a furnace, different type of furnaces. And we do the sizes. When I say we size the overcome protection device, we size the disconnect and we size the cable for them. Any comments, any questions, guys? Shall we have 5? Okay, thank you.